Hello, everyone. Welcome to today's webinar, Childhood Adversity, Resilience, and the Brain, with Dr. Andrew James. My name is Chad Sievers, and I'm the project manager for Arkansas Building Effective Services for Trauma, or ARBEST. So before we turn the presentation over to our presenter, I just want to tell you a little bit about ARBEST. We are a state-funded program at the University of Arkansas for Medical Sciences Psychiatric Research Institute. Our aim is to improve mental health services for children who have experienced trauma from events such as abuse, natural disasters, or family separation. We work closely with child advocacy centers and other providers in the state to build a trauma-informed mental health system, and are probably best known for providing training to mental health professionals and treatments that are effective in helping children recover from trauma. Through this training, in addition to direct services, technical support, and outreach in the community, we're helping transform the delivery of mental health services in Arkansas so that children and families who have experienced trauma can recover and move forward with their lives. I'm really excited about today's presentation. I want to go over a couple of housekeeping announcements. Advance the slide here. Oh. If you'd like to ask a question during the presentation, and we hope that you do, please use the question feature, which is on the right side of your screen. If you're interested in earning 1 CU, just be sure to stick around to the very end. We'll have a code that's given, and you'll need to email me that code, and more instructions will be given at that point. We are recording this webinar, and we'll upload it to our YouTube channel here. And if you like this, if this topic interests you, be sure to like us on Facebook. We frequently post our webinars there and other training opportunities. And also, we have a couple of handouts today that we hope that you download. There are a couple of research studies that are open seeking recruits, so you can read about information on that. And there's also a PDF of this presentation can be downloaded as well. So. All right, well, I wanted to let me introduce our speaker today. Dr. Andrew James received bachelor degrees in chemistry and applied psychology from the Georgia Institute of Technology. He received his doctorate in neuroscience from the University of Florida, where he used functional MRI to model age-related changes in networks governing motor learning. In 2009, Dr. James joined the Department of Psychiatry and Behavioral Sciences in the College of Medicine at UAMS here. As an assistant professor in the Brain Imaging Research Center, or BERC, he is establishing the cognitive connectome to explore how the brain's neural networks encode individual variability in personality and cognition. By understanding how the healthy brain encodes cognition, he seeks to translate this technology into patient care and better inform clinical decision-making. So let's all give a warm virtual welcome to Dr. Andrew James.
Hello. Hi. Thank you, everyone. It's a pleasure to be here today, and I'm very pleased to be able to talk to you about my research and its applications toward childhood trauma. Oh, sorry, I missed a slide. Okay, so I wanted to start off with the objectives or questions that I hope we can ask during this webinar. One question I'd like to help answer is, well, what are the biological consequences of having experienced childhood trauma? Similarly, what are the rates of resiliency against against childhood trauma, or having the negative consequences of childhood trauma? And does this resiliency itself have a biological signature that we can study? And finally, how can we use research such as brain imaging to study trauma's biological consequences and or the adaptive mechanisms that help promote resiliency against the negative effects of childhood trauma? So I think when discussing childhood trauma, it's important to focus on this seminal study conducted by the CDC in conjunction with Kaiser Permanente, known as the ACE study. Oh, and you should see also for all these slides, I have a a web link at the bottom where you can just click on it to get more information. I don't know if it's showing up on your screens or not, but it's there. So if you want to get more information about the ACE study or other studies, by all means, just follow those links. They're peppered throughout the presentation. So the ACE study by Vince Felitti was a study of adverse childhood experiences and their consequences. This is a pyramid showing how at the bottom we have adverse childhood experiences, which can have a broad range of negative consequences influencing health and well-being throughout the lifespan, from disrupted neurodevelopment to impairment in social, emotional, and cognitive domains, to the adoption of negative health or health risk behaviors, leading on to disease, disability, and social problems, and even early death. Now, for this study, they studied 17,337 participants who were insured by Kaiser Permanente, and they followed up on hospital visits, clinic visits, etc. these people had, and they wanted to relate their health conditions back to adverse childhood experiences. The adverse childhood experiences, or ACEs, were defined as types of abuse, either physical, emotional, or sexual, types of neglect, physical or emotional, and a variety of household challenges, such as having experienced domestic violence within the home or having a family member with substance abuse disorder, etc. And what the study found was that 2/3 of participants reported having at least one of these ACE scores, and that the ACEs had a cumulative risk factor. So having increasing number of ACE events, types of ACE events, were associated with greater risk for what we would consider psychiatric or mental illnesses like alcohol abuse, illicit drug use, suicide attempts, and depression, but also a broader range of just general health risks like having heart disease or liver disease, COPD, or having an STD. So this study was pretty provocative or game-changing, in that it pointed out that childhood trauma just doesn't have, in addition to the psychiatric negative health effects, there's also broader physical and biological health effects which need to be studied. So it really did raise awareness about early childhood trauma's long-term health effects in both psychiatric and non-psychiatric domains. But what about resiliency? What helps people resist the negative effects of these childhood traumas? And what's interesting is that approximately half of children who experience trauma end up being resilient against this negative outcomes. Now, I believe this is in reference to having a single event, traumatic event during childhood. Of course, as if you have more cumulative events, this would be different. But this is some work by George Bonanno and Diminich showing, as a review article that you can download for free from the link below. But they showed that longitudinally in a cohort of several hundred children, somewhere between 35 to 65% of children who experience a childhood trauma went on to be resilient against it, to not have long-term or short-term consequences up to 2 years out. About 5 or 10 had a spike of a negative response following the trauma, but then rapidly improved and were stable. Let's see. 15 to 25% had a longer negative consequences, but then that drifted off over time. And there's some delay. Some had delayed negative consequences. About 0 to 15% had a delayed outcome. And then there are individuals who had chronic dysfunction following the trauma, 5 to 30%, and then another 5 to 15%, which had just had continuous negative symptoms, where you see the chronic kind of comes and goes, but it's persisting. The continuous was more elevated across time. So there are a number of psychosocial predictors of resiliency. This is from a review listed below. And I'm probably the last person you want to be asking about what these psychosocial factors are. I just put up the slide to illustrate some of them. And you've probably had other webinars on this topic. Three psychosocial factors discussed in the review below are ego resiliency, or the ability to adapt to environmental stressors, ego control, or the ability to resist impulses when under stress, and self-esteem, the confidence in one's own worth or abilities. But I bring up these points to point out that there's also biological consequences of childhood trauma, as well as potentially biological predictors of resiliency. My apologies. So one biological example comes from epigenetics. As you know, genes are associated with a broad range of behavioral and clinical conditions. One example is grooming, a measure of parental behavior in animals. And I would say humans too, you know, grooming your children is a good thing. However, there are environmental influences that can in turn influence gene expression. For example, determining whether a gene is expressed or turned on or not expressed or turned off. And these epigenetic influences occur throughout the lifespan, but they're especially prominent during the period of early development. And I believe you've already had a webinar on epigenetics, but I included this very short video. It's about a 4-minute video to kind of give the broad strokes of epigenetics. So we're going to take a moment to watch the video so you get an idea about epigenetic influences and how they may play a role during trauma or early childhood trauma.
All right, so, and just as a kind of a preface, so the audio of the video is going to be played through your computer speakers. So if you joined via phone, just a heads up on that. Apologies if you have technical difficulties hearing the video. As Dr. James said, it's a short 4-minute video, so I'm going to get that started here.
All right, I think I'm back on. So the summary of that video is that while we have certain genes that we're born with, our environment can influence the expression of those genes, whether they're turned on or off, etc., and can lead to, so our early environment can have long-term behavioral consequences and lead to behavioral changes. Oh, do we, is that the right, 1 second? Okay, there we go, we're back on track. Okay. So there are some examples of epigenetics in humans. So cortisol and, I'm just going to say DHEA. Cortisol and DHEA are stress-responsive hormones which help to regulate our fight or flight instinct, help guide our behaviors in times of stress. And in animals, it's been shown that trauma exposure can lead to those epigenetic changes in the expression of cortisol, which in turn alters stress reactivity within animals. And so Cicchetti and Rogosh investigated in children whether diurnal cortisol levels and diurnal DHEA levels among 677 children, approximately half of whom had experienced maltreatment, to see if there was any evidence of epigenetic changes in the genes influencing these hormones. And I should say they're actually looking at the hormone levels and inferring epigenetic consequences within those varying levels of hormones. So they found some interesting evidence supporting that this was the case. So at the top we have a plot showing changes in DHEA during the day, and it had been shown in previous studies that aberrant changes in diurnal variation of DHEA could be associated with both having high anxiety or negative mood. And in the top, we have the group of children who did not experience maltreatment, subdivided into groups based on, I guess, social functioning, low functioning individuals, medium functioning individuals, and high functioning individuals. And we see that in the non-maltreated group, there's a similar pattern across all three. The diurnal variation from morning to afternoon is pretty similar. Interestingly, in the maltreatment group shown at the bottom, they found that low and medium functioning children had a similar pattern of behavior of diurnal DHEA levels, but a completely different pattern for the high functioning individuals. There was a sharp increase in DHEA levels from morning to afternoon compared to both the non-treated group and the other maltreated children of lower functioning. So this was some interesting biological evidence to suggest that yes, there could be epigenetic influences in children, or as a consequence of having experienced childhood trauma, which could provide resiliency against the negative effects of that trauma. A caveat, though, is that it's complicated, and if you read the paper in more detail, trying to relate these changes to individual differences in the functioning, it's a challenge to really put it all together in one just one framework. It's interesting that there are differences, but then trying to interpret the significance, the meaning of those differences, becomes a bit more challenging. So that's an important caveat to have when reviewing that work. So now we're going to move on to brain imaging, and here is a shameless plug for my group. Here in the Brain Imaging Research Center at the UMS Psychiatric Research Institute, we're interested in understanding brain function and how brain function leads to those individual differences. When we're looking at brain function, it's a bit more sensitive than other biological measures, so we can more directly, in my opinion at least, my professional opinion, more directly relate individual differences in cognition to patterns of brain activity, and perhaps better inform behaviors and cognitions with brain imaging. So there's a number of approaches that have been used to study brain imaging, and the one we focus on here, these approaches vary, and here, let's see if the cursor works, yes. These approaches vary in the time scale of data you can measure from millisecond to days, and they also vary in the size of the area to be studied, which can range from individual synapses to neurons all the way up to the whole brain. These imaging approaches also vary in their invasiveness. And in this schematic, this diagram, the lighter colors are less invasive. So having a naturally occurring lesion is the less invasive intervention or the less invasive form of study versus sticking something into the brain to directly measure neural activity. We're focusing on functional MRI, this orangish area, which is, and the reason fMRI gets a lot of research focus is that it's a good trade-off between the time scale, ranging from seconds to hours, although after an hour people are usually clawing to get out of the machine, so there's some limitations there, and the size of the area to be studied, which can range from individual cortical columns all the way up to the whole brain. And it's fairly non-invasive as long as you don't have any metal in you. If you're metal-free, there should be no consequences. I've had about 200, so knocking on wood, hopefully that there won't be any updates to that in the years to come, but it's pretty non-invasive. For the typical MRI experiment, we have a subject and we place them on a table and slide them into the bore of the MRI. While they're in there, we present them stimuli. So we may have like an image projection system so they can view images. We have a headphone system for microphones so they can hear us in between the scans and talk to us. During the scans, we can play sounds to them. They can respond to those sounds. We give them a button box, typically 4 or 8 buttons, so they can make motor responses based upon what they're seeing or hearing. And really, any sort of experiment you can think of that could be done in a psychology lab or in a that kind of environment, we can replicate within the MRI. We can do having people rate images, listen to different sounds. We can have them doing math or thinking about what they had for dinner. Any sort of experiment that you can think of. Someone has done it. In fact, when I was back at Emory, I helped develop a juice delivery device for a taste perception study. So people were lying on their backs of a long straw, tasting different types of sweeteners and non-sweeteners. So there's been a lot of innovation to try to move the psychology lab to the MRI environment. Now, while the subject's in the scanner, we take pictures of brain activity and then use that data to study what brain regions are active during different parts of the experiment. We do this by taking advantage of the molecule hemoglobin. Well, before that, we know we're looking at levels of oxygenation through the blood. We know that in response to a stimulus, there's neural activity which leads to an increase in blood flow of oxygenated blood flow to that area and increase in oxygenation. So the initial neural activity consumes oxygen and the body responds by shunting oxygen-rich blood to that area. And we know empirically that greater neural activity leads to greater blood flow. There's a lot of theoretical considerations as to, well, how exactly does this happen? And in my opinion, there's probably individual differences muddying that up. So I don't know that we'll ever fully understand all these different pathways. Well, we're making good progress toward that. But we do know that empirically, neural activity leads to blood flow, which leads to increases in oxygenation. And we can measure those changes in oxygenation thanks to the molecule hemoglobin. So as you may know, hemoglobin carries oxygen through the bloodstream. And each hemoglobin has 4 subunits, each of which has an iron core. And each of those subunits can bind a molecule of oxygen and bring it through the system. When oxygen is bound to hemoglobin, oxygen's electronegativity masks the magnetic influence of that iron core, and the hemoglobin is magnetically neutral. You can't see it with a powerful magnet like an MRI. But when hemoglobin gives up that oxygen, that iron core becomes exposed, and then we can see very tiny magnetic influences on surrounding tissue. So we can use that to infer neural activity. We do this, now the caveat is that there's always oxygen in the brain. To really do this experiment, you want to just get rid of all the oxygen, but obviously that would lead to death, so we don't do that. At baseline, there's some ratio of oxygenated hemoglobin to deoxygenated hemoglobin just circulating through the bloodstream. And then when neural activity happens, two things. First, some of these oxygenated hemoglobins are going to give up their oxygen. Now, if you look closely, some of these greens are about to turn purple. So there's immediately within a second of the neural activity happening, some of the hemoglobin that happens to be in the area will just give up its oxygen. So you see a very tiny change, but that's followed about 4 seconds later by an influx of oxygen-rich blood. So the ratio becomes even more distorted or more imbalanced with a high concentration of oxygenated hemoglobin coming to that area. So that's really the signal of what we can detect is this influx, we call it a bolus, an influx of oxygen-rich blood to that area. And from that, we infer that neural activity happened in this area. With MRI, oh, there it goes. Oh, hey, okay. Oh. So yes, so we're taking a snapshot of brain activity every 2 seconds. With newer devices, you can get a snapshot of up to half a second. And over time, for a given brain region, we can look at its change every 2 seconds in the oxygenation of blood in that area, and then infer, we can map those changes in blood oxygenation to a task that the subject may be doing. So in this example, we can have someone tap their fingers to elicit activity in the motor cortex. And here, the areas in red at the top are brain regions that were more active during finger tapping or had higher oxygenation during finger tapping than in the absence of finger tapping. And if you look at the bottom, this is the mean time series of all those areas in red. And you can see a very distinct pattern of greater oxygenation, i.e. neural activity when tapping your finger, compared to periods of time when you're not tapping your finger. So what do we know from brain imaging? What can we infer about potential biological contributions to resiliency? Some of this earlier research used EEG to study brain patterns as they may relate to childhood trauma. And the reason for that is for the MRI, it's crucial that the subject stays still. And when you're looking at young children, having them lie still for an hour on their backs with nothing to do can be a bit of a challenge, as some of you may well know. Fortunately, with EEG, you can put a electrode cap on a subject. These little dots represent individual sensors. You can see each one of these dots represent an individual sensor. And with EEG, you're looking at underlying electrical activity of the cortex. Well, you can go deeper than the cortex. You're looking at underlying electrical activity for each of those sensors. And EEG and MRI have different benefits. EEG has a much better temporal resolution. So with MRI, we're taking a snapshot of the brain every 2 seconds. With EEG, you can take 10,000 snapshots in a second. You can have up to like 10 hertz frequency. The downside, though, is that you have limited coverage, so it's harder to localize. With EEG, it's harder to localize where brain activity is occurring deep in the brain. It's much better at detecting surface activity than deep structures. Whereas with MRI, you're looking at oxygenation throughout the brain, so it has better spatial resolution or spatial localization. So there's a couple studies here. One by Richie Davidson in 2000. Broadly associated the left hemisphere with having positive emotions and the right hemisphere with negative emotions. Now, I was hesitant to even put that. This is such a huge oversimplification. I'm tempted just to strike the whole thing out, but this is one of the seminal, works of the field. So for historical reasons, it's important to include that. But please, don't quote me as saying that. This is such an oversimplification. It's like a sweater. When you start pulling at a thread, the whole thing unravels, but there's some evidence to support that. But more interestingly, Curtis and Chiletti in 2007 had some children with and without maltreatment, 87 children, approximately half of which had experienced maltreatment, undergo EEG, and they were looking at patterns of brain activity which may promote resiliency in the maltreated group. So in the maltreatment group, they were further subdivided into children with low functioning versus high functioning. And the high functioning group was identified as being resilient. They used, the question, well, how do you identify resiliency? For this study, they had a variety of measures. They had social report, peer report from other children. They had teacher evaluations. They had some self-esteem questionnaires, just a variety of measures, and then they conducted a big factor analysis to pull out a composite score which they believe represented resiliency. And what they found, interestingly, is that two factors had an interaction effect to predict whether or not the maltreated group would be resilient or not. One was having positive emotion regulation skills, and another one was a biological factor, having greater activity in the left side of the brain, specifically around the central 3 electrode, relative to this right central 4 electrode. Let's see my little cursor. Not close enough. Okay, so this ratio, having greater left-sided versus right-sided activity, seemed to predict whether or not, in conjunction with positive emotion regulation skills, predicted better outcomes in those children who had experienced maltreatment. Now, how can we follow up on this with fMRI? What evidence is there from MRI? Well, some work in our lab, I should have a sidebar. So our group is very interested in addiction, and specifically how early childhood trauma could predispose one toward a trajectory toward developing addiction or other psychiatric illnesses later in life. And this is a study we did back 2010 to 2015, looking at the inhibitory motor control and the effects of childhood trauma and or current addiction on performance in adults. For this, we use the stop signal task, which is a measure of inhibitory motor control. Now, for the stop signal task, the subject is trained to press a button as quickly as he or she can whenever a letter appears on the screen. And then a letter, and it could be any of the 26 letters, they appear about once a second. So down below, you might see like an X, followed by S, followed by T. Whenever those letters appears, you push a button. Now, sometimes for 25% of the trials, the letter appears followed by a box. A few milliseconds later, about 50 to 100 milliseconds later, a box appears around that letter. And this is called a stop trial, and the box is called a stop signal, hence the name stop signal task. So when a box appears around the letter, the subject is instructed to inhibit that response, to withhold making a motor response. And it gets tricky. You get in the rhythm of pushing the button quickly whenever a letter appears, and then suddenly a letter and a box appears and you have to hold back. We titrate these trials, so if subjects are doing really good on the task, the box, the box will slow down to make it harder, and if they're doing very poorly on the task, the appearance of the time that takes for the box to appear speeds up, so it's easier. You see letter in a box immediately versus a letter and a longer delay. So we titrate the trials, and we can use these trials to estimate for an individual subject his or her stop signal reaction time. So on average, how much time does it take? How much long is this delay in order to get a correct, accurate performance? And other research has related that stop signal reaction time to other forms of impulsive behavior, like, I guess it's on the next slide. Well, that's on the next slide. But what we know from neuroimaging in humans and in animals, that this right inferior frontal cortex is associated with successful inhibitory motor control. So this area in blue, I'm showing the left hemisphere, but it looks the same on the right hemisphere, is associated with inhibitory motor control. Although there are other regions, research has shown that lesioning the right inferior frontal cortex in animals leads to deficits on this specific task. Furthermore, humans with right inferior frontal lesions have poor inhibitory control than humans without those lesions. And we have a technology, repetitive transcranial magnetic stimulation, or RTMS, which uses magnetic fields to disrupt the neural activity of a region. And if you use RTMS to disrupt neural activity in the inferior frontal cortex, people have performance deficits on this stop signal task, but not on other just simple motor tasks and simpler tasks. Now, as I mentioned, this stop signal task is a measure of motor impulsivity, but it's also been correlated with other impulsive behaviors. And people with psychiatric disorders characterized by impulsive behaviors like addiction tend to show poorer performance on the stop signal task than healthy comparison subjects. So as I mentioned, we previously did research trying to figure out how childhood trauma, sex differences, and addiction could influence how the brain conducts inhibitory motor control. And here's the reference down here if you want to download it. We recruited 40 subjects, roughly half male and half female. Now, although we did recruit a sample with addiction, we didn't have enough female subjects with addiction to do a fair comparison. So for this particular study, we're just focusing on the healthy control subjects with or without childhood trauma experiences. And we define resiliency as not having current addiction or past addiction or mood disorders for this trauma-exposed sample. So when subjects performed the stop signal task, we saw activity of the following 6 brain regions. We saw both right and left inferior frontal cortex activity. There's a dorsal anterior cingulate and a more, dorsal anterior cingulate, that's this, and then a middle cingulate region, and a right and left supramarginal gyrus region. And that we also found no significant effects of having experienced childhood trauma or a sex by trauma interaction effect upon just performance on the task, supporting that these trauma-exposed individuals were resilient against its effects. But then we found a very interesting sex difference in sex by trauma interaction effect. So here we're using an approach known as structural equation modeling to map out the causal pathways within the brain. So how one brain region could drive activity in another brain region. Here we have the right inferior frontal cortex, which, as we discussed, is associated with strong performance on the task, as well as the left inferior frontal and a midline, the dorsal anterior cingulate region. And what we found is that there was, in females without trauma, there was this positive, green is positive, red is negative, so this positive influence of left inferior frontal to right inferior frontal when performing the task, as well as a double inhibitory pathway. So left inferior frontal was inhibiting performance on the dorsal cingulate, which in turn was inhibiting performance on the right inferior frontal. So 2 negatives make a positive, kind of an indirect pathway by which left inferior frontal could facilitate right inferior frontal activity. Among the women with trauma exposure, though, we found that this left to right pathway was gone. There's no, it didn't significantly exist. There's no evidence of it. Instead, we saw kind of a detour, redirection of activity of left inferior frontal increase or more strongly inhibiting activity of the dorsal cingulate, which in turn was inhibiting activity of the right and frontal. So again, two negatives make a positive, but two rights don't make a wrong, or wait, two wrongs don't make a right. So you have this kind of an overall net increase in the influence of left to right, and even in the absence of this direct pathway. Now in humans, though, I mean, sorry, in males, though, without trauma, we see they look different from the females without trauma. So whereas women had a positive influential pathway from left to right inferior frontal, males had a negative and a very strongly negative pathway of left inhibiting right. And we're digging into that to try to figure out what the heck that means. But what's interesting is that with trauma, we still see the same pattern as what we saw for the women with trauma. This left to right pathway is gone, and the left inferior is influencing right inferior again through this intermediate of the dorsal anterior cingulate. So it's very interesting to see this this what could be a cortical a reorganization or perhaps a compensatory reorganization following trauma. Now again, the caveat of this work is that it needs to be replicated. So this is an interesting finding that could pave the way for using other approaches like neuromodulation via RTMS to try to change brain function and thus change behaviors, but we need to replicate it. So fortunately, we do have funding to try to replicate this finding in an independent cohort. We are actively recruiting for participants. We need men and women ages 18 to 40 with or without childhood trauma, but no current or past addiction or mood disorders. I believe Chad provided a survey, but if you want to go to our webpage, you can read about this and our many other studies. I'd love to hear from you, or just call our Google Voice number. This rings like 8 different phones over here, so you'll leave a voicemail and we'll get in touch with you. But back to the show. So please help us to replicate our work. But what we really need to know to try to tease apart if this is like a adaptive reorganization of the brain or if this is a protective pre-existing factor that provides resiliency, we have to have longitudinal studies. And I want to bring attention to one really promising study, the ABCD study. This is the Adolescent Brain Cognitive Development Study. This is an initiative primarily led by NIDA, the National Institute on Drug Abuse, but also NIMH and other National Institutes of Health, to study 10,000 children here in the U.S. longitudinally from ages 9 to 10 until they hit 20. So this is a really intense study. There's sites all around the country. The closest site to us is in Tulsa. We threw our hat in the ring to be a site, and unfortunately didn't get it. But I think we would have had a good time of it. I think we would have been a good competitor for that. So, anyways, here we have these subjects every year undergo several hours worth of cognitive testing, as depicted here. They give saliva samples, they undergo brain scanning, there's interviews with the parents, there's all sorts of, well, I guess that's down here, as well as computerized assessments, and then every 6 months, 3 to 6 months, they get followed for the development of addiction, other psychiatric illnesses, etc. And then they get followed for 20 years or 10 years. So I think that studies like this will help get to the chicken or egg issue, although at the same time, starting at 9 or 10 is probably too late. You probably want to start earlier. So we're currently looking to try to get started at an earlier cohort, which might then segue into the ABCD study. So with that, we have about 10 minutes for questions. I'm happy to field anything. If I don't know the answer, I'll tell you I don't know it, but feel free to ask anything.
Yeah, thanks, Dr. James. I really appreciated sort of the background info on these brain studies that we all read, and just how does that actually work. So that's very helpful.
Thank you.
We had a question. I wonder if you could talk a little bit about the cognitive connectome project that you're starting here, and how will it inform clinical decision making, or what's kind of
Oh,
the vision, or just tell us more about that.
certainly, yes. So my interest is in individual differences. So much of this field has been dominated by group level studies. You take 30 subjects with condition X, 30 subjects without condition X, and see how their brains differ. But when you're trying to look at individual subjects, that's not that helpful. There's a lot of variance in how our brains are organized, even if you are with a given clinical condition. So my interest is in trying to map out individual differences, or how the brain encodes individual differences in cognition and behavior. So in addition to being appointed in the Department of Psychiatry, I'm also appointed in the Department of Neurology, and I'm interested in disorders like epilepsy, stroke, MS, which could lead to changes in the brain and in turn change cognition. So the Cognitive Connectome was an initiative that I started here with the Division of Neuropsychology, also here in the Psychiatric Research Institute, doctors Jennifer Kleiner and Jennifer Guess, to take the very comprehensive 4-hour neuropsych battery they're administering for all of the neurology and neurosurgery candidates and find MRI adaptations of that. So we took the tasks that they were doing in the clinic and had people do those same tasks in the MRI scanner, and then relate their standardized clinical performance to brain activity to try to tie those two together and map out individual differences, and eventually extend that toward trajectories of patients to try to inform patient care. Does that help? Or I can go into more detail, but
yeah, we have a couple other questions that have come in. So when a young child experiences long-term trauma for a couple of years and then is removed from the source of trauma into a quote-unquote healthy home, what is the recovery process, and how much recovery can occur in their brain?
That's a very good question. I don't know that we know that. I don't know, definitely from a brain perspective. There have been, I know there's research on looking at trauma outcomes behaviorally. But I don't know that we.
Have you done any studies or treatment using hyperbaric oxygen?
We have not, but we're always thinking about ways that we could try to change the oxygenation of the brain to enhance the signal potentially. Some people have talked about trying to give people caffeine pills before the scan. I'm kind of skeptical of that. And plus, you also want to reduce head motion, so you don't want to give them too much caffeine, then you won't get a clear signal at all. No, we haven't, but I'm going to look into that. That's an interesting idea.
So this is a follow-up question for me. So is the thought behind that, if there's more oxygen, then you'll have clearer pictures, and is that kind of the
yes. So yes. So since we're measuring oxygen flow or oxygenation of the brain, having more oxygen in so saturating the brain of oxygen may help with seeing that signal. It's really not so much the oxygen that's bound, but the oxygen that's given up. So, but I think in both cases, if you have a higher baseline of oxygenation, then I guess you have more oxygen to give up to the areas that need it. So you could, in theory, get a clearer signal. I'll have to work out the math on that and see. But I know, yeah. I'll have to look into that. That could work.
Okay. And just another kind of follow-up question from kind of related to imaging. Are you using SPECT imaging, SPECT imaging?
So SPECT imaging, yes. So SPECT imaging is that's a variant of PET imaging. So for that, it's a bit different. You give the subject a radionucleotide that then circulates through the bloodstream, and you can see where that radionucleotide goes. So for example, in PET imaging with FDG, it's a glucose-based radioisotope, and you just see what brain regions are taking up glucose. A downside of PET, of the FDG PET, is that glucose takes a long time, or the FDG tracer takes a long time to undergo radioactive decay and release its signal. So it's too slow a time scale to try to piece out what individual brain regions are involved in the cognition, because you can take a snapshot of brain activity over a 30-minute period, but that's too coarse to drill into what's happening from 1 minute to the next. Now with SPECT imaging, you can, since in that case you're injecting essentially like a dye that's emitting radioactive, gamma radiation, and you can measure that on a coarser time, on a finer time scale. But the downside is that all of that is you're dealing with ionizing radiation like what you would have in an X-ray. And with the MRI, it's all magnets. So as far as we know, there's no long-term harmful effects of being exposed to magnets. I mean, we get that exposure every single day, walk around outside. So no, we are not, but for our clinical collaborations, if we have subjects who, let's say they're a surgical candidate, they've had a clinical MRI, and they've had a PET imaging to try to localize the source of, say, a epileptogenic focus, we might, eventually down the road use that data to further inform our science. But here in the Brain Imaging Research Center, we're largely focused just on the MRI technology. But we are interested in moving toward other modalities, like there's near-infrared spectroscopy, which is similar to EEG, especially as we increasingly look at children. They move their heads so much, anything we can think of to try to keep their head still or use other modalities to study brain function, we're all ears.
Okay. We got a couple other questions in, but before I ask those to you, I just wanted to kind of mention our how to get a CEU if you're interested. So the code is up there, brain. You can email that to me. If you're watching as a group, please let me know who was the person that signed in to the webinar, just so I can verify attendance, and that's helpful. And if you tell me your first and last name, that just makes it easier for me to look you up and verify that you attended. So we'll have this up here. And we got a couple of other questions, Dr. James. Lesions on the brain was discussed and how it can cause poor inhibitory control. What are some things that could be a cause of lesions on the brain, in reference to this topic?
So that is, strokes or seizures, possibly either naturally occurring or drug-induced seizures. So those are the studies that I'm thinking of, where car accidents, MVAs, anything that could cause damage to the brain. But yeah, strokes, seizures, and physical trauma.
Okay. And we'll have this be the final question here. Or maybe this is a kind of a do you know of any? Does brain imaging reveal any neural activity as a child refuses to talk about their childhood trauma? What might potentially be reasons why a child might be guarded about childhood trauma? So are you aware of any studies measuring that?
That is, I'm not aware of any studies measuring that, but that's a great question. So our technology is increasing to the point where we can study patterns of brain activity, even if the subject doesn't tell you what they're thinking. We're getting to the point where we can predict what a person is thinking. Like if we show them a happy picture, we can predict how happy they're feeling. If we, give them a painful stimulus, we can predict how much pain they're feeling. So it could be, this technology, it kind of gets into some ethical considerations like lie detector tests. Can you give someone an MRI and tell if they're lying? The technology is not there yet, but there are people who are working on improving the methodology by which we can detect those unspoken patterns of brain activity. In fact, my colleague Keith Bush, also here in the Brain Imaging Research Center, if you go to the website, he's recruiting for his studies. He's studying how people process positive and negative emotions. And even if they can't tell you how happy they are, like, on a scale of 1 to 10, I'm a 7 or a 10, he's creating algorithms to figure out how the brain processes emotion and how it encodes those emotional experiences. So I think that there's definitely a lot of robust research in that area. We're not there yet. Given probably 10 years, we might be getting towards something like that.
All right. Well, it's always very interesting to hear you present, Dr. James, and I just want to thank you again. And for folks out there, if a question you think of later, just feel free to email me, and I'll be happy to pass those along. And again, just a reminder to download those research handouts. You can pass them out or read them, and this PowerPoint presentation is also available as a handout. So thanks again, and I'll leave this slide up for 30 or so seconds or so, and everyone have a great day.
All right. And Chad, thank you for organizing this. This has been a great experience. I appreciate it.
All right.